Hello everyone. So in this video, we are going to discuss the second problem which came in BMath 2008. So the problem says that you have a polynomial with real coefficients and suppose for some positive real numbers C and D, you have that for all natural numbers, this mod of Pn, this thing is bounded below by C times mod of n cube and by above by d times mod of n cube. So we have to prove that f of x has a real zero. So now let's see how can a polynomial be bounded. So the whole this question, the major part is like hidden here because there is no other thing like which might help us, only this real coefficients, and we have that this C and D are positive. Okay, so let's note this down, whatever we have, and yeah, so let's proceed. Okay, so it's given that Pn mod is greater than equals to C times mod of n whole cube, and it's lesser than equals to D times mod of n whole cube. So let's notice one thing, that is, suppose if P is a polynomial of degree greater than equals to 4, then what happens? So we have here am x to the power m plus dot dot a4 x to the power 4 plus a3 x cubed plus a2 x squared plus a1 x plus a naught. Now we have n here, so this relation is given in terms of Pn. So let's replace these x by n's. So we have n to the power m dot 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 till a4 n to the power 4 n cube n square a1n. Okay, so we have mod. And now let's do one thing. Let's divide this n cube on both the sides. So what we'll be having is, you see that this m will become m minus 3. And so this 4 will now become 1. The 3 will become 0. So we have n to the power 0 here, and then onwards we have 1 by n, and then we have 1 by n squared and 1 by n cube. Mod is lesser than equals to d and is greater than equals to c. Now c and d are given to be positive reals. Now notice one thing, that is in this relation, the middle one is being bounded by two constants, two positive constants. Now if you just simply let n tends towards infinity, then so if n tends towards infinity, then whatever is inside this, that will either tend to minus infinity or positive infinity. But since the modulus is given, this inside part will tend towards positive infinity. And so then we have a contradiction, that is the whole thing can't be bounded by d. So if n tends to infinity, then mod of Pn divided by n cube mod is tending towards infinity if degree of px is greater than equals to 4. Okay, so now if so that's a contradiction, so that means p of degree of px, so we get a contradiction, which implies that degree of px should be lesser than equals to 3. Now let's also notice one thing, that is, suppose if degree of px is 2 or lesser than 2, then what happens? Then we see that this okay, so then we have a x squared plus bx plus c. Now again I'll replace this by n. So okay, let's not use c and d, we have already got those as constant. So let's use a2x squared plus a1x plus a naught. Now let's replace those x by n, and we have to divide this by n cube. So when we divide this by n cube, so we get here 1 by n, here 1 by n squared, and here 1 by n cube. And it's given that mod of this thing is lesser than equals to d and greater than equals to c. Now notice one thing, that again, if n tends to infinity, then whatever be a2, a1 or a naught, this thing will tend towards 0 because they are fixed real numbers. So then mod of pn by n cube tends towards 0 if degree of px is lesser than equals to 2. So yeah, if it's lesser, if it's of degree 1, then you have a1 divided by n square plus a naught over times 1 by n cube. And if the degree is 0, that means if it's a constant one, so you have a naught 1 by n cube. So whatever it is, so the thing is that it tends towards 0, this thing, the middle part. And so we get that c is lesser than equals to 0. But c is a positive real number. So c is strictly greater than 0, and we have a contradiction here. And so degree of px has to be greater than equals to 3. Greater than equals to 3. So which implies that degree of px has to be equal to 3. And that basically implies that px is a polynomial of odd degree. And we know that px is a polynomial with real coefficients. So even if px has complex roots, so complex roots would occur in conjugate pairs, and thus at least one real root is guaranteed. And so we have at least one real root of px. Okay, so this is true for any odd degree polynomial. And thus we are done. Okay, so thank you for watching.